So let us start today's class and we will discuss in today's class Q meter and its applications and errors. So what is Q meter? We know that every inductor coil has a certain amount of resistance and the coil should have lowest possible resistance. The ratio of the inductive reactance to the effective resistance of the coil is called the quality factor or Q factor of the coil. So XL by R, which is equal to omega L by R. A high value of Q is always desirable as it means high inductive reactance and low resistance. A low value of Q indicates that the resistance component is relatively high and so there is a comparatively large loss of power. The effective resistance of the coil differs from its DC resistance because of eddy current and skin effects and varies in a highly complex manner with the frequency. For this reason, Q is rarely computed by determination of R and L. One possible way for determination of Q is by using the inductance bridge, but such bridge circuits are rarely capable of giving accurate measurements when when Q is high. So special meters are used for determination of Q accurately. The Q meter is an instrument designed for the measurement of Q factor of the coil as well as for the measurement of electrical properties of coils and capacitors. This instrument operates on the principle of series resonance, that is, under resonant condition of an AC series circuit, voltage across a capacitor is equal to the applied voltage times of Q of the circuit. If the voltage applied across the circuit is kept constant, then voltmeter connected across the capacitor can be calibrated to indicate or to read Q directly. So let us have how it actually works. A wide range of oscillator with the frequency range from 50 kilohertz to 50 megahertz is used as a power supply to the circuit. The output of the oscillator is shorted by a low, you can see the diagram of Q meter here. The output of the oscillator is shorted by a low value resistance, RSH, usually of the order of 0.02 ohms. So it introduces almost no resistance into the oscillator circuit and represents a voltage source with a very small or of almost negligible internal resistance. The voltage across the low value shunt resistance RSH, V is measured by a thermocouple meter and the voltage across the capacitor VC is measured by an electronic voltmeter. For carrying out the measurement, the unknown coil is connected to the test terminals of the instrument and the circuit is tuned to resonance either by varying the frequency of the oscillator or by varying the resonating capacitor C. Readings of voltages across capacitor C and shunt resistance RSH are obtained and Q factor of the coil is determined. So by definition, Q factor of the coil is given by what? Q is equal to XL by R. And when the circuit is under resonance condition, XL will be equal to XC. So it becomes XL is equal to XC is equal to VC. And the voltage applied to the circuit is equal to V, which is equal to IR. The Q factor is called the circuit Q because this measurement includes the losses of the resonating capacitor, voltmeter, and the shunt resistance RSH. So the actual Q factor of the coil will be somewhat greater than the calculated Q factor. This difference is usually very small and may be neglected except when the resistance of the coil under test is relatively small in comparison to the shunt resistance RSH. The inductance of the coil can also be computed from the known values of frequency F and resonating capacitor C. How it can be determined? At resonance, XL is equal to XC, already we know that. So 2 pi FL will be equal to 1 by 2 pi FC. So if you derive that, you will land up with L is equal to 1 by 2 pi F the whole square C Henry. See, you can measure, you can do the measurement of low impedance components as well as measurement of high impedance components too using Q meter. So let us have, even you can measure the bandwidth. Let us discuss or let us have in detail discussion about error in or various errors occurring in measurements. So first one is error due to distributed capacitance. The distributed capacitance or self-capacitance of the measuring circuit introduces error in the measurement and is the most important source of error. This source of error affects the actual value of Q and the inductance of the coil. Distributed or self-capacitance CD of a coil can be measured by making two measurements at different frequencies. The coil under test is connected directly to the test terminals of the measuring circuit, and resonating capacitor is tuned for resonance at two different frequencies, that is F1 and F2. So values of resonating capacitors B, C1 and C2 at those frequencies, what's that? F1 and F2. Now you will land up, if you derive and you will land up with the relation CD is equal to C1 minus 4C2 by C3. So distributed capacitance reduces the effective values of Q of a coil, and the difference between the measured value and the actual value depends on the value of the distributed capacitance and the resonating capacitor. The true value of the Q can be obtained from the relation Q is equal to QM of C plus CD by C. Second one is error due to residual inductance of the instrument. The error due to residual inductance of the instrument is very small and it is of the order of 0.015 microhenry, and so affects the measurement of only very small inductors, say inductors of value lesser than 0.5 microhenry. Next is error due to shunt resistor. The shunt resistor RSH of the Q meter circuit introduces error only when resistance of the test coil is comparable to the shunt resistor. Say for example, a coil of resistance 0.2 ohm is measured with shunt resistor of 0.2 ohm. Otherwise, error due to shunt resistor RSH is very small and can be neglected, as in case of measuring Q of a coil of the resistance 20 ohm with the shunt resistor of 0.02 ohm. Last one is error due to conductance of voltmeter. The error may be introduced due to shunting effect of conductance of the voltmeter connected across the resonating capacitor at higher frequencies. But this error is too small that it can be neglected also. So various applications of the Q meter, it is used to measure the quality factor of the inductor. By using this meter, unknown impedance can be measured using a series or shunt substitution method. If the impedance is small, the former technique is used, and if it is large, the latter technique is used. And it is used to measure small capacitor values also. And by using this Q meter, inductance, effective resistance, self-capacitance, and bandwidth can also be measured. So this completes the Q meter discussion.